This question is concerned with state feedback control. We're given a state space model that represents a dynamical system. Here we see, here's the x dot term, the a x plus b u, and y equals c x. And it's asking us first of all to analyze the open loop system just to make sure it is fully observable and fully controllable. Then it's asking us to, well, we're going to basically be designing a state feedback controller. So it wants us first of all to write down the corresponding state feedback control equations that we can get from basically the normal state space equations. And it wants us to use a gain vector k, which is built up from two elements, k1 and k2. So it's telling us that this is then it's going to be a 1 by 2 matrix with k1 and k2 being the element values. Then we want to design the controller, right, and put eigenvalues at -2 and -3. So it's now asking us to write down the characteristic equation corresponding to that kind of system. And finally, we're asked to calculate the gain matrix K. So it's asking us to design the controller effectively. So choose K, so we end up with a system the system that we started with that's then got eigenvalues at -2 and -3. So first of all, let's start off by looking at, this is quite a simple part. Let's look at the system, right? We've got x dot equals ax plus bu, y equals cx. So A is obviously going to be this matrix up here. B is this vector here, and C is this vector here. Okay. Now we're going to first of all look at controllability. So since we've got a 2 by 2 A matrix, we're going to only need two terms in our controllability matrix, and that's going to be B concatenated with AB. Now we know what B is already because we've got that straight off the system, but we need to calculate AB. So let's do that. We have to calculate AB. So so it's always rows by columns. 4 lots of 1, 10 lots of 1, that's 14. 2 lots of 1 plus 2 lots of 1, that's 4. We then concatenate those together, and as you can see, we're doing that as a horizontal concatenation. That's what this is telling us. This one followed by that one on in the next column. We end up with this expression here. Now, we can tell if a system is controllability if the controllability matrix is full rank, and full rank means that there's no linear dependencies in the system. So we haven't got a row which is basically just a scaled version of another row. And the way we can find that out is calculating echelon form. And echelon form means we want to get this system into the form that, in this particular case, this lower left-hand element goes to 0 by taking off scaled versions of other rows. And we've only got one other row, right? So what we do is we say we want the new row 2 to be the row 2 we've got now, take away row 1, because then we have a 1 minus a 1, and we've got a 4 minus a 14, and that's what we're doing here. So we calculate this, and we end up with 114, 0 minus 10. And as you can see, we've got echelon form, there's a 0 here, but this row does have a value in it, right? So it's not a null row, therefore we have a rank 2 matrix, and therefore the system is controllable. Let's now look at observability. Again, because it's a 2 by 2 A matrix, we only need two terms in our observability matrix. This time they are concatenated right, vertically. So we've got C and CA. Again, we know what C is, but we don't know what CA is off the top of our head, so we have to work it out. So it's going to be, as again, rows by columns, this times that. So 1 lot of 4, 0 lot of 2s, 1 lot of 10, 0 lot of 2, so 4, 10. And then we concatenate vertically. So this is the C, this is the CA. And again, we need to say, is that full rank? And we can only work that out by taking away scaled versions of other rows in order to actually see whether or not it all disappears and goes to 0, or is whether or not there's something there, in which case the system is not linearly dependent. So to get rid of this, we have to take away 4 lots of the first row, right? So it's row 2, right? The new row 2 becomes the row 2 take away 4 lots of the first row. So 4 take away 4 is going to be 0, and it's going to be 10 take away 4 lots of 0, which is going to be 10. And we end up with a matrix 1, 0, 0, 10. And clearly there are no 0 rows in there, therefore the matrix is full rank, therefore the system is fully observable. So we've got our system. What we're going to do now is apply state feedback control. So we're going to set u equals minus kx, okay? And k is going to be of the form k1, k2. So it's going to be this row vector, and we'll come to that in a second. But basically what it's asking us to do now is just to say, you know, we've got the state space equations. Here's the state space equation for x dot. We want to substitute u in as minus kx. That's all it's asking us to do for this part of the question. So we stick in u equals minus kx, so we end up with ax minus bkx, and we factorize out the x, and we get the new modified relationship, x dot equals a minus bkx, and this is then basically the state update equation when we use full state feedback control. And in this particular case, the system, obviously the eigenvalues is determined by the a minus bk matrix, as opposed to in an uncontrolled system where they're determined by the a matrix. So the next bit is to say, look, we want a system now which is going to have poles or eigenvalues at -2 and -3. So what is the characteristic equation of a system like that? And the characteristic equation is basically the solution equation to the eigenvalues. So when does this equation basically has got to equal 0 when we hit eigenvalue values of -2 and -3. So we have to write a simple equation down which is going to do that. And if we multiply lambda plus 2 and lambda by 3 in 2 brackets equals 0, that will achieve this, because if we set in this equation lambda to -2, the first term goes to 0, so it's true. If we set it to -3, the second term goes to 0, so it's true. So that's the goal equation. We can then multiply it out and get the terms, the powers of lambda coming through. So lambda squared plus 3 plus 2 is 5 lambda plus 2 3s are 6. So that's basically the characteristic equation that we want to get to when we analyze our system and find the k. So the eigenvalues of the closed loop system basically are going to satisfy the equation that the determinant of a minus bk minus lambda I equals 0. So a matrix, b and the k matrices, and lambda times the identity matrix. Now we have to substitute in b. In fact, we have to substitute in bk. So let's calculate bk. It's going to be the b vector multiplied by the k vector, and we've been told that we should put in k1 and k2 here. Just a little note here, you know, what form is b times k, and we can see that we're taking it away from a. So a is 2 by 2, so bk has also got to be 2 by 2, because otherwise we couldn't calculate it, right? So it's just a reminder. So this has got to be a 2 by 2. So that's what we'll get, because it's always rows by columns. So it's row by that, then row by that, row by that. So we're going to end up with a 2 by 2 matrix. So it's 1 lot of k1, 1 lot of k2, 1 lot of k1, 1 lot of k2. Next thing to do, we've got to solve this equation now for k. So we have to put in the values that we've got for a, put in the values we've got for bk and lambda I. So like I said, I is the identity matrix. So what we do is we stick them all together. I'm now using these vertical lines to represent determinant. And what we do is we just evaluate this, right? So it's just the first term up here is this element, take away that one, take away that one. It's an element by element subtraction. 4 minus k1 minus lambda, right? That's what we've got here. This is 10 minus k2, there's no term here. This is 2 minus k1, that's what we've got here. And then we've got 2 minus k2 minus lambda, that's what the last term. Then to calculate the determinant, I haven't written it here, but basically this is a 2 by 2 matrix, so it's going to be A times C, take away B times D, right? That's the determinant of a 2 by 2 matrix, and that's got to equal 0. That's what we're saying here at the top. So we write this times this, that's that bit here, and then this times this, that's that bit here. It doesn't matter what order we do them in. Next thing to do is to multiply out so we can collect up terms of lambda. So we've got lambda squared, we've got k1 plus k2 minus 6, lots of lambda, and we've got this constant term here. Now, what we want to do now is find out what k1 and k2 are, so we end up getting the same characteristic equation that we said we wanted when we find a system with eigenvalues of -2 and -3. So what we have to say is the characteristic target equation, lambda squared plus 5 lambda plus 6, has got to be equivalent to this thing that we've just come up with. And by doing that, we can then find out what k1 and k2 are, right? So we just basically have to say the 6 here has got to be equivalent to this term here, 8k1 minus 2k2 minus 12. And the second one is saying, look at this term here, 5, right? 5 has got to be equivalent to k1 plus k2 minus 6. So we've got the two simultaneous equations. So we first of all, we rearrange the first one, and we end up with k2 equals 4k1 minus 9. We can then stick that into the second equation, and we substitute that in, so we've got it all in k1s. So in goes this there, right? And then we have k1 plus 4k1 minus 9 minus 6 equals 5. And that will give us a k1 equals 4. And we obviously then can calculate k2, which is equal 7. So we've come up with the gains by doing that.